Welcome. Next, we are going to do an improper integral that comes up in statistics and also in queuing theory. But as a warm-up to that, we are going to do a simpler version of the same problem. This is to evaluate improper integral of e power 2x dx from negative infinity to 0. Recall how we defined improper integrals when one of the endpoints of the interval is infinite. In this case, I have negative infinity. I replace that by r and then take the limit as r goes to negative infinity. To calculate the proper definite integral from r to 0, I am going to use the fundamental theorem. So I have to find an antiderivative of e power 2x, but you can use our extended rule for exponentials. Since the base is e and the exponent is a number times x, an antiderivative is the exponential divided by the coefficient in the exponent. Now I take the net change from r to 0, plug in 0 for x and then plug in r for x and subtract. E to the 0 is 1, so I get 1/2 minus e to the power 2r over 2. Now I have to let r go to negative infinity. Recall the limits of exponentials. In this case, I have r going to negative infinity. As r goes to negative infinity, 2r also goes to negative infinity. And since the exponent goes to negative infinity, e to that power goes to 0. So the integral is 1/2 minus 0, or just 1/2. Now we are going to do the problem, which as I said turns up in statistics. It's to find the number k, so that the integral from 0 to infinity of k e to the power negative lambda x dx is 1, where lambda is also a constant. Of course, the answer will depend on lambda. Basically, we are going to calculate the improper integral from 0 to infinity of e power negative lambda x dx, and k will be its reciprocal. It's very much like the previous example. We also have to assume that lambda is positive. So again, recall that to define this improper integral, we replace infinity by a variable. In this case, I'm using r, and we let r go to infinity. So I'm going to do the proper definite integral first. Since k is a constant factor, it stays as it is, and our extended rule for exponentials applies. And since the base is e, all I get is the exponential divided by the coefficient of the variable in the exponent, in our problem negative lambda. Then I take the net change, so plug in r for x and then 0 for x and subtract. And then I'm going to simplify this. In the second term, I have k times e to the power 0. That's just k, because e power 0 is 1. And then I have two negatives. I can combine them to a single positive, so I get k over lambda. In the first term, I have some constant times the exponential. Now I want to take the limit of that exponential. Remember that lambda is positive. R goes to infinity, then the exponent goes to negative infinity because of the minus in front. So that limit is 0. The integral itself is just k over lambda. And that equals 1 if k equals lambda. So in other words, the integral from 0 to infinity of lambda e power negative lambda x dx equals 1 as long as lambda is positive.